Hello all, welcome to next video on image enhancement. Uh, in this lecture we will discuss image enhancement in frequency domain. In last two videos we have discussed image enhancement in spatial domain. So to come from spatial domain to frequency domain we would require a tool. So that tool would be Fourier transform. So Fourier transform would get us the frequency spatial domain to frequency domain. Now let's discuss how do we get the frequency domain of a signal which is fx, that is in spatial domain. So fx, the Fourier transform of fx is given as integration minus infinite to infinite fx e raised to the power minus j 2 pi ux, where x is the spatial domain variable and u is frequency domain variable. That means we can say u is the frequency and x is the spatial domain variable. Now the inverse of this fu is given by inverse Fourier transform formula, that is given by fx is equal to integration minus infinite to infinite fu e raised to power j 2 pi ux. So here e raised to power j 2 pi ux is called the eigenfunction of Fourier transform. Now here we use minus while calculating the Fourier coefficients, and here we use plus while calculating the inverse Fourier transform, and these two formulas are called the Fourier transform pair. Okay, now since the image signals are two-dimensional signals, so if we have to find the Fourier transform of a two-dimensional signal, so fxy is two-dimensional signal, so it is x is one dimension and y is another dimension. So corresponding to x we will have frequency component, that is frequency variable, that is u. Corresponding to y we will have frequency variable, that is v. So the Fourier transform of the spatial domain, two-dimensional spatial domain, is given by this formula, and the inverse of this is given by this formula. Now these are the formulas of the spatial domain to frequency domain if spatial domain signals are continuous signals, but image signals which we use and we perform operation on are discrete signals. So if we have to perform the frequency domain analysis on the discrete signals, then we have to take discrete Fourier transform of the signal. Now discrete Fourier transform of a signal fx is given by 1 by m summation x varies from 0 to m minus 1 fx e raised to power minus j 2 pi ux by m. Now here we can have this fx is analogous to this fx. This is the eigenfunction as we had eigenfunction here, and this will be multiplied by 1 by m. Now here 0 to m minus 1, that means we have total m number of samples of the spatial domain fx signal, and we will get the same m number of samples in the frequency domain too. So the size dimension of the signal will be same in the frequency domain also. Now the inverse Fourier transform of this fu can be given by this formula. That means using the inverse Fourier transform formula we get the original signal from the Fourier coefficients. Now these are the discrete Fourier transform formula pair. Now since this we can look at this signal is actually complex signal. So complex signal can be given as its by its magnitude and its phase. So complex signal can be represented as modulus of fu, that is amplitude, e raised to the power minus j phi u. Phi u is phase of this signal. So the modulus is given by r square plus I square whole under the root, where r is real part of fu, I is imaginary part of fu. The phase of it is given by tan inverse I by r. So this magnitude is known as Fourier spectrum and the phase is known as phase spectrum. Now since power is analogous to the square of the magnitude. So the square of the magnitude would be r square plus I square. So this is called as power spectrum of the signal. Now moving ahead, we have, now since this we have discussed about the one-dimensional discrete signal, but image is two-dimensional discrete signal. So we will discuss the two-dimensional discrete Fourier transform, that is DFT, and its inverse. So in one dimension we had only one independent variable in spatial domain. So here we will have two independent variables, x and y. The corresponding to x we will have frequency variable u, and corresponding to y we will have a frequency variable v. So fuv, that is frequency domain signal of corresponding to fxy, is given by 1 divided by mn summation x varies from 0 to m minus 1, y varies from 0 to n minus 1, fxy e raised to power minus j 2 pi ux by n plus vy by n, and its inverse is given by this formula. Now we need to see this, that the x is also varying from 0 to m minus 1 and y is varying from 0 to n minus 1, and we know the dimension of the Fourier coefficient, that is DFT signal, will be same as the dimension of the spatial domain signal, that is fxy. So it will also vary from, u will vary from 0 to m, and v will vary from 0 to m minus 1, and v will vary from 0 to n minus 1. Now if we want that the origin of this Fourier coefficient should be shifted to the center of the plane of the image, then we multiply the Fourier the original image by minus 1 raised to the power x plus 1, sorry, x plus y, minus 1 raised to the power x plus y. Now if I want to find the Fourier transform of this signal, that is f xy multiplied by minus 1 raised to the power x plus y, so its Fourier transform will be given by f u minus m by 2 and v minus n by 2. So fuv is the Fourier transform of fxy, fuv is the Fourier transform of fxy. So the Fourier transform of fxy multiplied by minus 1 raised to the power x plus y would be f u minus m by 2 and v minus n by 2. Now multiplying this signal by minus 1 raised to the power x plus y, what we have achieved? We have achieved that we have shifted the origin of FUV. The origin of FUV. Origin means when U is 0 and V is 0. This origin of FUV we have shifted to the center of M cross N area occupied by 2D DFT. What would be the center of occupied area? So now you see the image is M cross N, so it would have some center. So since image is m cross n, so FUV also will be m cross n. So it will occupy some area, and the center of that area would be given by the m by 2 and n by 2 coefficients. So the origin of this FUV we have shifted in the center of that area. So this is what we have achieved by multiplying this original signal by minus 1 raised to the power x plus y. Now let us see what happens. What do we get at the origin of this frequency domain signal? That means when u is equal to 0, v is equal to 0, what do we get? When u is equal to 0 and v is equal to 0, f00 is equal to 1 by mn summation x ranges from 0 to n minus 1, y ranges from 0 to n minus 1, fxy, and this term would become 1. Why? Because u is 0 and v is also 0, so this term will become 0, sorry, 1. So what would this summation give us? This summation will give us the average gray level of image. This is average gray level of image. So what is happening here? You see, x we are varying from 0 to n minus 1, y we are varying from 0 to n minus 1. That means we are considering all the rows and all the columns, and then we are adding all the intensity values, all the gray levels we are adding, and this we are dividing by total number of pixels. That we are dividing by total number of pixels. So if the dimension is m cross n, then the total number of pixels will be m into n. So we are dividing it by the total number of pixels. That means we are getting the average gray level of the image. So that means at the origin of this frequency domain signal, that is frequency domain signal FUV, we will get what? Average gray level of the input image. Now this, as we have discussed previously, this is the frequency spectrum of the output signal, this is the phase spectrum, and this is the power spectrum of 2D uh, discrete signal. Okay, now how do we perform filtering in the frequency domain? That comes next. Now frequency is related to rate of change. Frequency is related to rate of change. So we know that slowest varying frequency component. So slowest varying frequency component means the frequency is not at all varying. That means u is equal to 0 and v is equal to 0, corresponds to the average gray level of the image. Average gray level of the image. This we have calculated here. So this is the average gray level of the image, and so this is also called DC component of the frequency domain. DC component of the frequency domain. Why it is called DC component? Why? Because both the frequency variables are zero in this. Both the frequency variables are zero. That means there is no frequency available in the signal. Only DC component is available. So this is called DC component of the image, and this represents the average gray level of the image. Now as we move away from the origin, then we move away from the origin means we are changing the value of u and v. That means we have the low frequency components. Low frequency components will correspond to slowly varying components of image. That means low frequency components will represent slowly varying gray levels of the image. Slowly varying gray levels of the image. As we move further away from the origin means we have the larger values of u and v. That means larger values of frequency. So that represents higher frequency, and higher frequency correspond to faster rate of change of gray levels. Faster rate of change of gray levels. So as we go away from the origin, that represents faster rate of change of gray levels. Now these are the edges, the higher frequency components. These are the edges of the objects and other components of the image with abrupt changes in the gray level, such as noise. So the edges in the image and the edges in the image and the abrupt changes in the image are represented by the high frequency components of the Fourier transform, that is FU. Now this is the image, and this is the Fourier transform of this image. So here this image is multiplied by -1 raised to the power x plus y. That means its origin is shifted to the center. So I was talking about this, that here is the origin if we do not multiply it by -1 raised to the power x plus y. So here is the origin. Now when we multiply it by -1 raised to the power x plus y, its origin will shift here at the center of this DFT plane. This is the DFT plane, its center is here. This is the origin of the image. So origin of the image, here this value represents the average gray level of the image. So here you see this represents the average gray level of the image. Now near to these frequency components, here these frequency components, here we are varying u, here we are varying v. So here these frequency components will have lesser value of u and v. So these components are known as lower frequency components. And here at the boundaries of this image, they will have higher values of u and v. So they corresponds to higher values of the frequency, higher values of the frequency. Now you see here, this image has the higher average value. Since it has more white pixels, more bright pixels, so it will have high average gray level. So high average gray level is there. So you see here it is represented by a high intensity. And since you see it has these slowly varying gray levels areas, slowly varying gray level areas, you see here we do not see any abrupt change in the gray levels. Here also there is no abrupt change in the gray level. So here we see more coefficients are there which have the lower frequencies. Now it has the edges which are extending at the 45-degree angle from this axis. So it is extending at the 45-degree angle. So you see these angles which are extending at the 45-degree angle, and they will have the higher frequency coefficients also. Here you see these represents higher frequency coefficients, so these edges have the higher frequency coefficients too. And we know the higher frequency coefficients represents the edges in the image. So edges in the image. So this is how we perform. We convert the spatial domain image into the frequency domain image. Now how do we perform the filtering? So we follow these 6 steps to perform any filtering operation on the image. So we multiply the input image by, the first step is we multiply the input image by -1 raised to the power x plus 1 to center the transform as indicated in equation this. That means we multiply it by this one so that the origin will be moved to the center of the transform, Now we compute FUV, the DFT of the image. Now we convert this spatial domain signal into the frequency domain. That means we calculate the discrete Fourier transform of the input image. Then we multiply FUV by the filter function. So filter function is given by HUV. That means we multiply this input image by filter function. Then we compute the inverse DFT, that means inverse discrete Fourier transform. We compute of this multiplication result, and then we obtain only the real part of this inverse DFT coefficients. We take the real part of this. Why we take only the real part? Because when filter coefficients are positive and real, and filter coefficients are real, and the image coefficients are also real, then the imaginary coefficients will be negligible. So we can neglect those imaginary parts, and we take only real part of the result. Then we multiply the result uh, obtained in 5 by -1 raised to the power x plus y. Why? Because we had multiplied it in the first step. So we again multiply it by -1 raised to the power x plus y, and we get the enhanced image or the filtered image. So HUV is called filter because it suppresses certain frequencies in the transform while leaving others unchanged. Now you see FUV or UV is the frequency domain signal. So it is multiplied by HUV. Now in HUV we will have coefficients such that it will suppress certain frequency, either low frequency or high frequency. It will suppress, and it will leave remaining frequencies as it is. So that is why we call this a filter. Now Fourier transform of output image and filter image is given by, so Fourier transform of output image would be this. So this is the Fourier transform of input image multiplied by filter coefficient, filter function. We get the what? The Fourier transform of output image. And if I want to find the output image, filtered image, the filtered image will be inverse Fourier transform of this. That is inverse transform of this would be filtered image. So these are the 6 steps we follow to perform frequency domain filtering on an image. Now a more generalized diagram of frequency domain filtering is shown here. So here we have input image. We perform some pre-processing on it. We perform some operations, maybe cropping or scaling of the gray level that we perform in the pre-processing. Then we take its Fourier transform. So we get Fourier transform coefficients FUV. Then we multiply it by filter function. FUV is the filter function. So we multiply it by filter function. We get HUV, FUV. Then we take inverse Fourier transform of it and we perform some post-processing operations. In post-processing operation, maybe it is the multiplication of minus 1 raised to the power x plus y. That is post-processing operation. And then we get here the enhanced image. So this is a simple block diagram of frequency filtering in frequency domain. I hope it is clear till this. Then let's take some examples of frequency domain filtering. So first filter we have is notch filter. So the notch filter is defined as it is equal to 0 if UV is equal to m by 2 n by 2. So it is equal to 0 when UV is equal to m by 2 n by 2. That means the origin we have the coefficient filter coefficient 0 at the origin of the image, and it is 1 otherwise. That means we are suppressing the origin coefficient and we are keeping the other coefficients as it is. That means what we are doing, at the origin we have the average of gray level of image we have at the origin, so that we are suppressing and we are keeping all the other frequency coefficients as it is. So what will happen in this, the average gray level of the original image, so the original image was like this. If I subtract the average gray level from this image, then the average gray level will become 0. Average gray level will become 0. Now to have average gray level 0, we need to have negative intensity values, negative gray levels. Now since we cannot display the negative gray levels, so what is done is the average gray level is reduced to 0 and the negative most negative gray level is represented by 0. So that is how this image is displayed. This is how this image is displayed, and this filter would set F00 to 0, leaving all other frequency components untouched. So it is making the origin to 0 and remaining all components are as it is. Processed image can be obtained by taking inverse Fourier transform of FUV and HUV. That means HUV multiplied by FUV. This will be the filtering operation, and inverse of this will give you the filtered image. It is called notch filter because it is constant except 0 at origin. So it is 0 at origin and except that it is 1, so that is why it is called notch filter. Now there is a drop in average gray level in the image. That is quite understandable. Why? Because we are removing the average gray level from the frequency coefficients. So if I take the inverse Fourier transform of multiplication of Fourier coefficient multiplied by this, so the average gray level will be subtracted, that will be eliminated from this. So that is why the image is appearing darker here, and remaining all the coefficients are intact. That means lower frequency coefficients and high frequency coefficients are available in this. So we can observe in this image that the edges are clearly visible in the image. Edges are clearly visible in the image because we know the edges are represented by higher frequency coefficient in the frequency domain. So they are clearly visible in the output image. Now next, if we have to perform the low pass filter and high pass filtering. So in low pass filtering, what do? We pass the low frequency component and we suppress the high frequency components, and we do reverse in the high pass filtering. So this is a two-dimensional low pass filter. So we know that at the at the center of the plane we have low frequency, we have the DC component, and near to this we have the low frequency components. So here we are multiplying the low frequency components by some value, and we are multiplying the high frequency components by 0. So this is called a low pass filter. So in low pass filter, the output will have less sharper details. The output image will have less sharper details. That means, you see, after performing low pass filtering on the original image, here we can see that the sharper details are not much visible. That means the edges in the image are not clearly visible. They are uh, lessened in this output image. Then high pass filtering, what do we do in the high pass filtering? We remove the low pass filter coefficients, we remove them, and we maintain the high pass high frequency components. We maintain the high frequency component, and we reduce the low frequency component. So here you see the coefficients of low frequency are very less in magnitude, and the coefficients of high frequency are high in magnitude. So when this filter is multiplied with the Fourier coefficients of the original image, Fourier coefficients of the original image, then you see the higher frequency coefficients will be enhanced, and DC coefficient and the low frequency coefficients will be removed, or they will be reduced in the image. So what will happen? The high pass filtered image would have less gray level variation. It will have less gray level variation in smooth areas, and emphasize transitional gray level details. Transitional gray level details means edges. If there are sharp changes in the image, that will be emphasized in the image if we perform high pass filtering on the image. Such images, such image will appear sharper. So here this image is sharper. So this is the output of a high pass filter. Okay, so thank you. That's it for this lecture. We will meet in the next lecture.